Hello, good morning. So this is the title of our paper 2, Gravitational Astrophysics, Magnetism and Magnetostatistics for this semester. So the syllabus of Unit 1, that is what we are going to see. Gravitation, here we see Kepler's laws of planetary motion, only statement, Newton's laws of gravitation, relation between G, capital G and small g. Capital G is the universal gravitational constant. G is the acceleration due to gravity, gravitational field, gravitational potential, Gauss theorem, gravitational potential and intensity due to a uniform solid sphere at a point inside and outside the sphere, gravitational self-energy of a galaxy. So here the Kepler's laws of planetary motion. The first law states that all the planets move around Sun in an elliptical orbit, having the Sun as one of the foci. So this is the first law of put forward by the Kepler in around say 1609. So as I said, Earth is moving around the Sun and it is moving in a elliptical orbit. All the planets are moving in a elliptical orbit with the Sun is one of the fourth. The second law states that a radius vector joining any planet to Sun sweeps out the equal area in equal length of time. So, as shown in figure, the Earth is moving around Sun. We have taken the example of Earth as a planet, and this is the position of the Sun. So Earth is revolving around the Sun like this. Okay. So while revolution, the area swept by the radius vector. Radius vector means the line joining the Earth and Sun. Okay. So area swept by the radius vector is same for all the time. That means, for example, in 1 month duration, the Earth moves from here to here. So area swept will be A1, and for other side we can say here if the earth moves from here to here during 1 month, the area shift here is A2, then A2 will be equal to A1. So this is the second law. This law was also put forward by Kepler in around say 1609. But the third law was put forward after 10 years of the first and second law, that is 1619. Okay, that is the important law. The Kepler's third law states that the squares of the periods of revolution of the planets are directly proportional to the cubes of their mean distances from the Sun. That is, T square is directly proportional to R cube. So these were the statements of all the Kepler's laws. So let us see the Newton's law of gravitation. So the Newton's law of gravitation states that any particle of matter in the universe attracts any other particle with a force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So if let us consider the two masses having mass m1 and m2, if the distance between them is say r, then force is directly proportional to the product of masses m1 and m2 and inversely proportional to the r square. Okay, so if proportionality sign is removed by the equal to sign, a proportionality constant can be added, and that is equal to g. G is called the universal gravitational constant. So Newton's law of gravitation can also be put in the form say like this. Let us have say masses say capital M and small m. We are going to see capital M in this chapter. We take it as a mass of Earth, and small m is the mass of any other object. So Newton's law of gravitation can be put as F is equal to gmm upon r square. Okay, so where J is the universal gravitational constant, whose value is equal to 6.673 into 10 to the power minus 11 Newton meter square per kg square. Its SI unit is Newton meter square per kg square, and its dimensions of universal gravitational constants are L cube, m to the power minus 1 and t to the power minus 2. So let us take one example. Say determine the force of gravitational attraction between Earth, where mass is 5.98 into 10 to the power minus 10 to the power 24 kg, and a 60 kg physics student. If the student is in an aeroplane at 40,000 feet above Earth's surface, this would place the student at a distance of say around say 6.37 into 10 to the power 6 meter from Earth's center. So 1 feet is around say 0.3048 meter. If you convert that, that comes out to be around say 12,200 meters. Okay, so if you add this distance to the radius of Earth, you will get the value of gravitational force. Or simply you may calculate the force of gravity by using simple formula. Mg is the weight of the student. We can say Mg is equal to 60 into 9.8. 9.8 is the acceleration due to gravity on the surface of Earth. Okay, so that comes out to be 5.88 Newton. Okay, so if you put the data in the formula, F is equal to gmm upon r square, so that will be a little difference. It comes around say 590. Okay, so you may check that. Okay, so Newton's law of gravitation can also be put in the vector form, because force is a force is a vector quantity. Force is a vector quantity that must be put in a vector form. So here in the diagram, say m1 is the mass having position vector say r1, and m2 is another mass having position vector say r2. So vector r2 minus r1 is this vector joining m1 and m2. Now here the force is attractive. That means m1 is attracted by m2 and m2 is attracted by m1. So this is pulling force. Okay. So let us define force. There are two forces. M1 is acting on force m2 and m2 is acting force on m1. So F12 is the force on m2 by m1, and F21 is the force on m1 by m2. F12 and F21, these are the equal and opposite forces, attractive forces. So F12 can be expressed as G m1 m2 upon r square into vector r2 minus r1 upon mod of r2 minus r1. So it can also be expressed as F12 is equal to G m1 m2 upon r cube into r2 minus r1. So F12 is equal to G into m1 m2 upon magnitude of r2 minus r1 cube into r2 minus r1. So these are the several ways one can express the force in vector form. Okay. So similarly, F21 can also be expressed as G m1 m2 upon r1 minus r2 cube mod of r1 minus r2 cube into r1 minus r2. So r1 minus r2 is equal to minus of r2 minus r1. So F12 may be or say F12 is equal to minus of F21. So here Newton's third law is followed. So this is about the Newton's law of gravitation in vector form. So let us see the relation between G and G, that is universal gravitation constant and the acceleration due to gravity on the surface of Earth. For that, let us consider the mass on the surface of Earth, mass m, small m, on the surface of Earth. It is attracted towards the center of Earth. The capital M is the mass of Earth, R is the radius of Earth. So weight is acting on the mass m. Okay. So G is the acceleration due to gravity on the surface of Earth. Capital G is the universal gravitational constant. M and R, capital M and capital R are the mass, which is mass of Earth is 5.98 10 to the power 24 kg, and radius of Earth is 6357 kilometer respectively. M is the mass of mass on the surface of Earth, any mass m, small m. So here weight of the body of mass m is equal to gravitational force acting on it. So if you put the values, gravitational force and weight, so mg is equal to gmm upon r square. If you cancel small m on both sides, you will get the value of g, that is acceleration due to gravity on the surface of Earth is gm upon r square. So its value, it comes out to be 9.8 meter per second square. Okay, you may check it that. So let us see the relation between capital G and GH. Now GH is the acceleration due to gravity at height h. So if you take this mass at height say h, so what happens? Here the acceleration due to gravity will change, and that acceleration due to gravity at height h is denoted by GH. G is the universal gravitational constant. Mass of Earth and radius of Earth is already defined. So let us see here, weight of the body is again equal to gravitational force acting on it. So here mgh is the weight of the body acting on it. Okay, so gravitational force becomes g into m upon r plus h square. So here the distance is now r plus h. The distance between the two bodies will be r plus h. So generally these distances is measured from center to center. So again here, if you cancel small m on both sides, you will get the value of gh as gm upon r plus h whole square. So let us see the relation between gh and g. We know that g is equal to gm upon r square and gh is equal to gm upon r plus h square. So here gh upon g is equal to gm upon r plus h square into r square upon gm. So gm cancels, so we will get gh is upon g is equal to r square upon r plus h whole square. So we may write like this, gh is equal to r square upon r plus whole square into g. So this is the relation between acceleration due to gravity at height h and acceleration due to gravity on the surface of Earth. So gh may be put in the form g into r square upon r plus h whole square. As I said, gh is equal to s. So this is just rearrangement. We have divided that r square which is in numerator to the denominator. So if you solve this and neglecting the higher term, that is h square term can be neglected because h is very small as compared to r. So if you retain only two terms after squaring, so you will get the expression like this. So g into 1 upon 1 plus 2h by r, and if you take that into numerator, that will become like this. So you will remember this expression, gh is equal to g into 1 minus 2h by r. Okay, now if you take the mass to the height, then the gravitation acceleration due to gravity will change. Okay, so we have taken that, we have seen that the g is the acceleration due to gravity on the surface and gh is the acceleration due to gravity as we go away from the surface. Okay, now let us see what happens if you go inside the earth. Okay, here from this expression it is clear that GH is always less than G. GH is always less than G. So if the mass is taken inside G, so GD is the acceleration due to gravity at the depth. Okay, so if the depth is say D, so mass is here. Okay, so this is the entire earth and mass is taken here at the depth D, and the radius, now the distance between these two bodies, that is center of earth and this body, will be r minus d. Okay, now the force acting on this small m, force acting on this small m is due to this mass of the earth only, because the rest of the mass, the force due to rest of the mass will be cancelled. Okay, so there is a force of gravity because of these two bodies, m and this part of the earth. Okay, so let us imagine, or say let us imagine that this part of the earth having mass say m dash. Okay, so m into gd, gd is the acceleration due to gravity at this position at depth d, is equal to g into m dash is the mass of this part of earth. Okay, mass of this part of earth is m dash into small m upon r minus d whole square. R minus d is the distance between these two objects. Now if you solve this, now what is m dash? M dash must be calculated. M dash must be calculated as a by using density. Okay, if the density of earth is rho, then m dash will be equal to 4 by 3 rho into 4 by 3 r minus d whole cube. Okay, then rho is equal to, if it is density, rho is equal to mass of earth upon volume of earth. Okay, so if you put the values of rho, then the m dash becomes equal to m into r minus d whole cube upon r cube. So here gd will be equal to, okay, so if you put this value here, then after cancelling this small m both sides, so gd will be equal to gm into r minus d whole cube upon r cube into r minus d whole square. So here it is cube and it is square, so after cancelling this you will get finally gd is equal to g into r minus d upon r. Okay, because gm upon r square, gm upon r square is equal to g. So out of this r cube, r square is included in g and remaining r will be here. So this is the expression for the acceleration due to gravity at depth d. So finally if you solve this, uh, okay, this r upon r is equal to 1 and minus d by r, so gd is equal to g into 1 minus d by r, and here also gd is always less than g. So we have now two expressions, gd equal to g into 1 minus d by r inside the earth, and gh is equal to g into 1 minus 2h by r. The variation of g with respect to this is the distance from the center of earth. So on the surface of earth g is maximum, that is equal to g, so this is the variation of gd. Okay, as on the surface of earth its value is g, acceleration due to gravity is g, and when the, if you go into the depth towards center, it's this decreases, acceleration due to gravity decreases, and if the height is increased then also it decreases like this. Okay, it is parallel. Okay, so this is how g varies with the distance from the center of the earth. Okay, the remaining portion we will see in the next lecture.